Good morning, everybody. I'm Anna Silenzi. I'm architect and consultant for the World Health Organization. During this presentation, we will focus on how natural ventilation for infection prevention and control and climate control strategies for user comfort were addressed in the design of the 3 multiple infectious disease treatment centers in Uganda. But let's do a step back. Why ventilation is so important in the context of infectious disease? Well, ventilation moves fresh air, normally outdoor air, into a building or a room and distributes the air within the building or the room while the stale air is removed. The general purpose of ventilation in buildings is to provide healthy air for breathing by both diluting the pollutants originating in the building and removing the pollutants from it. In case of respiratory disease where airborne transmission may occur, ventilation is a key strategy to reduce the risk of infection in the indoor environment, since we should consider the pathogen as the pollutant of our indoor air. What does it mean, dilution? Let's imagine a glass of red wine. The more fresh water we pour inside the glass, the more transparent the wine glass will become, because we are diluting it. The same principle could be applied to the room. Let's imagine a hospital room with a patient affected by respiratory disease inside it. The more time he spends inside the room with window and door closed, without ventilation at all, the more concentrated will be the presence of the pathogen, as we can see from the top right illustration in this slide. As soon as we open the window and fresh air flows inside the room, the polluted air becomes more and more diluted as our glass of wine, of red wine, with the water. For this reason, the airflow rate is a key requirement in the context of the infectious disease. The airflow rate is usually expressed as liter per second per person, or air change per hour, or cubic meter per hour. The WHO recommends specific ventilation rate in case of respiratory diseases. In healthcare settings, the following minimum hourly average ventilation rates should be provided for infection prevention and control. 160 liters per second per patient for airborne precaution room, where aerosol generating procedures are performed in naturally ventilated spaces. 12 ACH air change per hour for mechanical ventilated spaces. And 60 liters per second per patient for general wards or outpatient department in naturally ventilated spaces, and 6 air change per hour for mechanically ventilated spaces. There is another aspect of ventilation that allows for infection risk reduction: the control of the airflow direction. The airflow can be controlled with several strategies, including both natural and mechanical means. The important aspect is that air should always flow from the most clean area of our hospital to the less clean area. For example, from the staff zone to the patient's zone toward outside. Ventilation system can be classified according to the airflow driving force. Indeed, there are 3 methods that may be used to ventilate the building. Natural forces drive natural ventilation. Mechanical fans drive mechanical ventilation, and mechanical forces combined with natural forces drive hybrid or mixed mode ventilation system. The decision whether to use mechanical, hybrid, or natural ventilation for infection control should be based on different aspects: on the needs, on the availability of the resources at the local level, and the cost of the system, including future maintenance to provide the best control to counteract the risk. Specialized engineers should be involved in the design process to ensure the optimal performance of the ventilation system. Actually, this is not a simple decision, but should be evaluated case by case according to the specific scenario and the specific local condition. The 3 projects for Uganda rely on natural ventilation. In many low-resource settings where funds for system maintenance are not ensured along year, natural ventilation is often preferred to the mechanical one. So, when a building relies on natural ventilation, the occupant's behavior play a key role. Natural ventilation, to be an effective engineering control measure, should guarantee user comfort as well. For instance, ensuring adequate temperature. For this reason, the building design should carefully include in the same strategy ventilation and building envelope design according to the local climate condition. An example of a bad behavior is a building that is not well designed and windows are closed and the air conditioning unit is switched on. In that case, we are controlling the temperature, but we are not allowing for ventilation inside the room. And this is a behavior that we want to discourage. And for this reason, it's really important to design a good building envelope. Ventilation study developed for the treatment center in Uganda aimed at considering as requirements the WHO minimum requirements for the airborne precaution in terms of airflow rates and airflow direction within the facility. Regarding the selection of construction materials for indoor temperature control strategy, particularly attention was paid on sustainability and local community engagement. The outcomes of the study are context-specific, but the methods of work could be replicated for other contexts. The first step of the ventilation study methodology applied in this project sees the microclimatic analysis of the construction site with the aim to decide the main orientation of the building in the site. The microclimatic matrix showed how the context could impact the project site in terms of making the most out of the sun and the wind resources. Optimize building orientation within the site, a windrows analysis has been conducted to highlight the most common wind direction during the daytime, while with the sun shading chart plot, the position of the sun in the sky linked to the dry bulb temperature, red the hottest hour and in blue the coldest hours highlighted in the diagram, to identify shadowing strategies to prevent overheating or enhance sun radiation collection during the coldest hours. 2 areas require particular attention as the most likely area where cross-infection may occur. The waiting area, where we have suspected cases waiting for triage and testing, and the patient room, where staff spend time with the confirmed cases. For the patient entrance, we opted for keeping the waiting area as an open air room. Keeping the proper distancing between chairs, the risk of being infected here is very low. Of course, we could propose an open air waiting area because the local climate condition allowed it. Looking at the treatment ward, and especially the patient's room, each of the room environment uses a different ventilation strategy. The bedroom environment uses a system of ventilation chimneys, one for each patient's room, windows oriented outdoor and vent under each door to provide minimum ventilation if the window is closed. The different opening height allow the stack effect to be exploited. Bathroom is ventilated by a single-side ventilation strategy. It has a unique window over the external world. They are fully separated from the central staff corridor that relies on natural ventilation as well. To assess the performance of the building, simulations were undertaken through specific software that allowed to calculate the air change rate of every single environment of the healthcare structure on an hourly basis. Simulations were performed for the entire building. However, in this presentation, we'll focus on the result considering the bedrooms only that are the most critical environment of the entire facility. In particular, since the wind has a primary direction, a windward room and a leeward room were considered in the study. For each site, the simulation has been conducted for the worst week of the year in terms of outdoor temperature and wind speed. The study then focused on patient room, and thanks to the support of simulation, we were able to adjust the layout and the opening design considering context-specific constraints like temperature. We may have in this area cold winter and hot summer. We had to consider the windows kept closed during the night for climatic and cultural factors and the presence of mosquito net in the opening. In this proposal, the patient room with the same dimension for all the three sites is characterized by 80 per 150 centimeter windows as inlet and 100 by 100 centimeter chimneys to expel the contaminated air. Furthermore, 30 by 80 centimeter section of the window was simulated as vent to allow minimum ventilation if the remaining part of the windows are closed, for instance, during the night. As already mentioned, the building ventilation should be included in a broader and holistic design strategy that encompasses the building envelope, the construction material, the structural elements. Indeed, the presented proposal envisioned a wall system that is critical to the effectiveness of the natural ventilation and thermal comfort proposed. Such walls are proposed to be made of high massive material, like raw earth blocks. Those can be stabilized with a 7-8% of cement to close all the micro voids in the block and developing waterproofing feature to increase durability and decrease the maintenance in future. For the roofing, a structural concrete slab covered with a corrugated metallic panel have been proposed. A ventilated air gap has been considered between the metal finish and the structure to decrease the temperature of the roof during the summer days. For the roof and the exterior paving, lighter color should be preferred to reflect as much as possible the solar radiation and prevent both the indoor overheating and the heat island effect outside the facility. Materials were also selected to be easily found at local level or easily product at local level. For instance, the earth block could be also created on site by involving the local community. In conclusion, we can say that good design may influence the occupant's comfort, patient care and recovery, patient and staff safety, community acceptance. And we can also say that good design needs a multidisciplinary approach and multidisciplinary expertise as well. Thank you.